Hello and welcome to another exciting lecture for stats. In this lecture we will be talking about distributions of data. So pretty basic stuff. We're just now going to look at how you present data. So as a preview of what we're going to do on this slide, we're going to look at distributions of data with the learning objective explain why we use descriptive statistics. We're going to look at data presentations, looking with learning objective number 2, demonstrate proficiency with data presentation methods used in this class. Learning objective 3, discriminate between bar graphs and histograms. So those are two specific data presentation methods. And finally, we're going to look at frequency distributions quite in depth. So that gets us to learning objective 4, be able to construct a frequency distribution. So let's start with a first look. And basically what you see here, at least with 23 rows, is what you can expect to see when you're presented with data. You get an ID variable here, you get a categorical variable here, a continuous variable here, another categorical variable, and then it looks like a sensitivity score, so probably a self-report or even on a different scale, and probably Likert scale 1 to 7 here. So you've got these variables and you've got all these numbers, and we can look at this and look and see, maybe look at age and see that it looks like the youngest is 21. Most of the people on this are in their young 20s. There's a couple that are a little bit older, but it really, when we're looking at it with only 23 rows, we can get a little bit of an idea what's going on. But what if you had 1,000 participants or 10,000 participants? Let's say you were looking at census data. Just looking at this first look really doesn't give you enough. It doesn't give you enough information about what you're seeing. So data in this form, it can be difficult to interpret and understand. So what we need is a more efficient way of organizing it. Rather than just having numbers that are spread out throughout the data set, we need something more clear, or a clearer way to read and understand it. And this leads us to exploratory data analysis. So exploratory data analysis is a set of procedures for arranging and displaying numbers that allow the researcher to quickly organize, summarize, and interpret data collected from research. So in a sense, it's a way of taking that spreadsheet that I showed you on the previous one and boiling it down to a few easy to understand numbers or graphs. So it's going to allow the researcher to take a first look at the data. It's going to provide descriptive statistics, which is those numbers I was just talking about. I'm going to throw this out there though. It can still be misleading. That is why we do inferential statistics, which we'll talk about later in the semester. But we do that because just having a descriptive statistic can be misleading. If I give you a mean, let's say I'm looking at the score that you got on a test, and there was two different tests, and let's say the mean on one test was a 60 and the mean on another test was a 6. What does that mean? Well, until you know the range, it could be that the mean of 60 was 1 to 1,000, or it could have been 1 to 100, or it could have been 1 to 60 and everybody got a perfect score on it. Until you know the range, you can't fully trust the descriptive statistics because they can be misleading. That 6, it could have been on a test out of 1 to 6, 1 to 10, 1 to 100. If you've got a mean of 6 on one test and it's 1 to 100, and a mean of 60 on another and it's 1 to 100, then that 6 is much lower. But that 60 on a 1 to 100 and the 6 is on a 1 to 7, that 6 is actually higher. So you really need more information. You need a measure both of central tendency, you need a measure of dispersion, you need a range, all of those types of things. Let's even get into that. So our single best value to describe our data, the single best value is this measure of central tendency. This is where you're going to get like the mean, the median, the mode. The central tendency, something that singly defines the data set. It's not enough by itself, but it is the single best value to describe it. And we'll cover that starting next week. The next important thing you need, because you can't do anything with a measure of central tendency without it, is a measure of variability. So, or a measure of dispersion. So it's how spread out the data is. So is it all clustered around the mean? Is it spread out a long ways from the mean? That type of thing. And we'll cover this in the chapter starting next week as well when we look at variance and interquartile range and those types of things. Also important is the shape of the distribution. And this is where you'll get skewness and kurtosis. And we'll talk about those as well in the coming weeks. And basically, skewness is how symmetrical the distribution is. If you put a mirror, if you cut the distribution in half and put a mirror on it, does that shape in the mirror look like the shape that you're covering up? So the more symmetrical it is, the lower the skewness is. We'll talk about that later, exactly what that is. Kurtosis is a measure of basically how clustered the data is. So if it's clustered towards the middle, it'll have low kurtosis. If it's spread way out, it'll have high kurtosis. And then, also important, is there a relationship between the variables being studied if you've got more than one variable? And this is where correlation will come in. And we'll look at this after the first test. So a correlation is also considered a descriptive statistic. It's a measure of essentially the relationship between two variables. Central tendency is where the middle of one variable, and correlation is essentially how two variables relate to each other. Let's get to the second learning objective, which is to demonstrate proficiency with the data presentation methods used in this class. The methods we're going to use are stem and leaf plot, though I'm only going to talk about that briefly, and I'm not going to expect you to do it again after that. But then we've got bar graphs, histograms, frequency curves, and what we're going to spend quite a bit of time with, which is frequency distributions. Before we get to those, though, and I'm going to have slides for each of those, before we get to those, let's first talk about the general rules for graphs. So these fundamental characteristics of a graph. First, you're going to have two axes drawn at right angles. The horizontal axes, or the x, and the y-axes. So you need to then label them. And we'll get to in a minute, you don't necessarily have to label them x or y if you've got variable names for them. The independent variable is going to be plotted on the x-axis. So the independent variable is going to be on the x, the dependent variable is on the y. What if you've got two dependent variables? What if you're doing correlational analysis and you've got two dependent variables? Which one goes on the x, which one goes on the y? That's up to you. You can put them in either. You can flip them if you want. It comes out the same either way, whether the first dependent variable is on the x and the second's on the y, or the first one's on the y and the second one's on the x. The length of the x-axis should be about 4 to 3 of the y-axis. So it should be the x-axis should be a little bit longer than the y-axis is high. I'm not going to get out a tape measure or anything. I'm not even going to measure anything like that. I'm just stating here what it should be. And the variables must be clearly labeled, both the x and the y. Let's say we were trying to see the effects of test preparation on anxiety. So we would label this preparation and anxiety. And then we would have to have, let's say it was a Likert scale. We'd have to have this labeled like this. And then we've got, let's say, minutes studying. So we've got 15, 30, 45, 60, then it's not being exact, but 75, 90, 105, that type of thing. So you need it accurately labeled. And the graph should contain all of the information needed to understand the data and nothing more. So in a sense, what you want to do now is get rid of these things that aren't important to understanding what's going on, and you're just left with preparation and anxiety with the numbers there. I'd move preparation down here a little bit so that it's able to understand it a little bit better. But you get the point. Everything needs to be labeled, and nothing extraneous, nothing extra needs to be there. And this is your general rules for creating a graph like this. Again, I'm not going to grade you specifically on how well you did on the graph. I'm just talking about what you should do, the way it should be. You don't have to memorize these rules, but you do have to know this is the x-axis and this is the y-axis, and that if you have an independent and a dependent variable, the independent variable goes here, the dependent variable goes here. I know I'm just adding back what I erased, but yeah, I think you get the point there. Let's look at the first of the graphs then, and this is the stem and leaf plot. And with this, what I'll say is that I'm not going to, this isn't going to be on your homework, it isn't going to be on an exam. I just kind of want to show this because this is a way to present data. It is a way that's used to present data. And essentially this is used when you've got multiple different numbers that you're presenting, multiple different digits. So in this case, we're looking at exam scores for 41 students, and these exam scores are 2-digit. So this right here is a 38, because you take the number before and then the number after, 38. Like up here, this is a 77, and over here, this is a 70. So you see that I would arrange them the other way. I'd put the zeros over to the left so it goes up, but you can do it either way. Like for here, this is a 99, 99, 98, 97, because you take the number that's before and put it with the number that's after. And then this is handy for displaying data when you're talking about displaying scores like this on an exam, when you're displaying a lot of things that have at least 2 digits. It's not used that often though, so just to be aware, it's not what's typically used. This does work a little bit better if you've got multiple instances of the same numbers, so you can easily see that there's like 2 99s. Here there's 3 88s, that type of thing. Let's go to one that is actually used much more, and that is the bar graph. So the bar graph is a graph in which is representing nominal or categorical data. So this is data that is, when you're looking at, like when you see here, car manufacturer, Ford, Honda, GM, Chrysler. So that along the bottom you have your nominal or your categorical variable, and that is basically what this graph is showing, is these different categories. It's very important though that these bars do not touch. You see there's a gap between the bars. The bars do not touch because they represent qualitative data, categorical data. It's discontinuous. There's nothing in between them. Plus, you can rearrange these however you want. You could put Honda first, Ford second, Honda at the end, Ford at the end. It doesn't matter which one goes where. And that's another reason why they don't touch, is because they are basically, in a sense, independent from each other. There is no one is greater than the other. They're, again, categories. It's nominal data. So there's gaps between them, and it doesn't matter which order you put them on the line. As far as the y-axis here, it can be a bunch of different things. It could be percentages. It could be frequencies. And that's what you're seeing here. That's what this f of x here means, frequency. We'll look at this on the frequency distribution that we'll do later. But the f of x is frequency. In a sense, that's what these are. So their frequencies you could take in, technically they're percents, because frequencies have to have a decimal. So 10% is at this line, 20 is at this. Oh, actually, these are straight frequencies. Ignore what I just said. These don't have dots. These aren't relative frequencies. They're straight frequencies, and a frequency is just a count. So this is 10, 20, 30, 40, 50, 60. So it's the number of cars sold by type. So you can look here and see that Ford, it looks like about 22, 23 were sold. Honda, 40 were sold. GM, 30. And Chrysler, 50 were sold. And you can have a bunch of different things. You could have percentages over here. You could have relative frequencies, which again we'll look at when we come to the frequency distribution. But the point is with a bar graph, the bars are separated because it is representing categorical data or categories. Conversely, a histogram, which is similar to a bar graph but different, is used to represent ordinal, interval, or ratio level data. And you notice the big thing here is, because it's a quantitative variable, the bars do touch. They don't have to. Basically what's going on here is that's 0. It's representing 0 that are in that range. It looks like we're looking at about ranges of 5 here with this histogram. We're looking at, like, this is 80 to 85, 85 to 90, 90 to 95, and 95 to 100. So in the range of 60 to 65, there were 0. And if we were to go back to the stem and leaf plot, I can't go back to it while I'm doing the recording, unfortunately. But if we'd go back to the stem and leaf plot, there were no scores between 60 and 65. The went from 58 to 66. So that's why there's none here, and those bars don't touch, because there were 0 instances of that. But in the other cases, if we looked at, let's say, this last one here, I'm looking at it on my other monitor, there was, in the high 90s, there was 2 99s, a 98, a 97, 2 96s. So we've got 1, 2, 3, 4, 5, 6. Looking at our count here, our frequency, we've got 6. So that's how that came about. And if you've got continuous variables instead of discontinuous, like these exam scores were all discontinuous. If you recall, what that meant is basically you could only have whole scores. You couldn't have decimals. But if they are, let's say it's a continuous variable, what is represented down here is the midpoint of a continuous variable, or of a class interval, which will explain what that is coming up in a little bit. But it's, let's say, an interval of scores like this is. This is the range of 95 to 100 here. These are intervals of 5. They are class intervals of 5% percentage points, or 5 points on these exams. And if you've got a continuous variable, this is basically representing the midpoint of it. So if we were doing, let's say we were doing weight along the bottom, because weight is a continuous variable, remember you can have weight that goes to many, many decimal points. It just matters that your level of measurement. If the scale you're measuring with is only whole pounds, that's considered the midpoint of that class interval. So when we talked about the real limits last week, the real limits are the limits around the midpoint of that number. And then one thing you can have as well, and this kind of goes over the top of the histogram, is a frequency curve. And a frequency curve is just essentially going to track at certain points frequencies, and then it basically maps on, you see here that this one's above and these ones are below because it's mapping on more of a continuous measure where you're looking at the averages as it goes through. So it's something that you can really only do with a computer program, and it's one of those things you'll be able to do in SPSS is you'll be able to throw a frequency curve over the top of your histogram. You just have to click a couple extra buttons and you can get to that. So let's look at just that in a little bit more detail, but now we get to this learning objective 3 to be able to discriminate between bar graphs and histograms. So I've talked about this in detail, but again, remember you use a bar graph for nominal level data, qualitative or categorical variables. We use a histogram or frequency curves for ordinal, interval, or ratio level data for quantitative variables. And again, for continuous variables, values on the x-axis of histograms and frequency curves are midpoints of those class intervals. So just remember it's midpoints in the middle of the real limits of those classes. Very basic there. What's the difference between a bar graph and a histogram? Mainly that bar graphs are used for nominal level data, histograms are used for ordinal, interval, and ratio, and bars don't touch, bars touch. So next, let's talk about frequency distributions. And for the rest of actually this lecture, we're going to be talking about frequency distributions. So that we're to the final learning objective, which is to construct a frequency distribution. There's going to be a whole bunch of slides that are going to be basically each step of constructing a frequency distribution. Let's say we were given these numbers here. Lots of numbers here, a 0, 2, 2, 2, 3, 3, 3, 3, 4, 4, all the way up to 10. A frequency distribution is going to take these numbers and basically show us how often each of these numbers occur. It's going to show us how often each of these numbers occur in relation to the whole. It's going to show us the percent chance of each of them occurring, the percent chance as opposed to a whole, all of those types of things. So when we look at this, we can see that there is 1, 0. As far as ones, there's actually 0 ones. There's none there. But 2, there's 3 of them. 3, we're going over here, there's 4 of them. 4, there's 1, 2, 3, 4, 5, 6. 5, there's 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. 6, there's 1, 2, 3, 4, 5, 6, 7. 7, there's 4 here. 8, there's 3, 9, there's 2, and 10, there's 2. So we can get an idea right now of the frequency of each of those. But now we're going to put it into graph format. But this is basically what I just wrote there, this 1, 0, 3, 4, 6, 8, 7, 4, 3, 2, 2. That's the frequencies for each of those numbers. That's what you're going to see as the first line in our frequency distribution. So a frequency distribution, the first thing we do is a frequency, or the number of times a score occurs. The number of times each score occurs. And if, let's say, you've got a continuous variable, on the previous slide I used a discontinuous variable. I only had whole numbers, and so for this example we're going to be using a discontinuous number. But let's say you had a continuous number like weight, and you were just categorizing the amount of people that were at each weight. Or let's say you were weighing something specific going on, and it was each one's weight. Well, what is actually going on if you've got a continuous variable like that is you're counting the number of scores that are between the upper and lower true limits of the interval that you're looking at. So let's say you're looking at like weights of different plants. You've got plants and you've got them in pots and you're weighing each of them, and one comes out to 6 pounds, another one comes out to 6 pounds as well. That doesn't mean they're both exactly 6 pounds. If you're only weighing it with whole numbers of pounds, that means they're all between those upper and lower true limits, which we did last week. So they're between 5.5 and 6.5 pounds. So that's what it means when, if we've got a continuous number, our frequency distribution is counting the number that are between the upper and lower true limits of that interval. We're going to denote frequency like this, f of x. You'll sometimes see it like this as well. In mathematics, you sometimes see this as function of x. We're talking about it as frequency of x. In parentheses, you could basically say of x. So if I did f of y here, it's frequency of y. But we're going to denote this because we're using the x variable. We're going to do f of x. So this is our frequency distribution. You can see there's a lot of rows that we haven't done. First, this is our x variable. This is the variable that you're given. Remember a few slides ago when I had that full out, I had the 0, there was no 1s, but then there was 3 2s all the way across the board. Well, that's what these, and it went all the way to 10. X went from 0 to 10. That's what this column is denoting, is the x's from 0 to 10. So each x gets its own row. First you've got 0, then 1, then 2. Now, your f of x, your frequency, is how often each of these numbers occurs. You recall from 2 slides ago that 0 down here occurred 1 time. That's why you've got a 1 there. If you recall, there was no 1s. There was 3 2s. 4 3s, 6 4s, 8 5s, 7 6s, 4 7s, 3 8s, and if you remember, there were 2 9s and 2 10s. That is how a frequency distribution is distributed. Now, I thought there was 41 scores. 2, 4, 5, 6, 7, 8, 9, 10, 11, 26, 36, 40. Nope, there was 40. I thought there was originally 41 scores. I must have deleted one to make it easier. A few slides ago we were talking about 41 scores, but now we're talking about 40 scores. So the n equals 40. You'll recall n is the number in our sample. N equals 40. The number of scores is 40. Down here at your total, if you add all of these up, you should get that number 40. So if we added that 2 plus 2 plus 3 plus 4 plus 7 plus 8 plus 6 plus 4 plus 3 plus 0 plus 1, you get 40. And this is the first step of a frequency distribution. I'm spending a little bit extra time on this step because this is the step that some people get confused with. It gets easier after this. If you understand that this column over here is the actual x values, the values that you were given in that distribution of scores. And this here is the number for each of those x values. So specifically, let's just look at this in the middle, this 5 and 8. What does that mean? You had the x score 5. There were 8 instances of the x score 5. There were 8 5s. So the frequency of 5s is 8. The next thing we're going to talk about is cumulative frequency. And cumulative, as you would understand, is going to be a adding. We're going to add to that point. And the way we do adding is we do the amount of scores at or below this point, or at or below that specific point. One thing you'll notice, the way I constructed it, and I'll get to that in just a second, I'll show you in just a second when we switch slides, but the way I constructed it is I counted the scores down from highest to lowest. So at the top of your frequency distribution is your highest x score, all the way down to your lowest x score at the bottom. You should always start with your lowest X score unless you have a logical reason to start at a different point. So let's say your scores ranged from 1 to 10, you would start at 1. But let's say your test was a 10-point test. So you could get anywhere from 0 to 10, but nobody got 0, 1, or 2. Or nobody got 0 points. You may still want to put 0 in it because even though nobody is at that point, nobody is at that lowest point in your distribution, it is a possible score. So you may want to include that. But as far as what you guys do, it's up to you how you want to do it, how you want to start it. You should either start at the lowest number in your distribution or start at the lowest possible you can get if it's logically makes sense for that. So what's next is the cumulative frequency, and that is the total frequency of scores, just like we did before, total frequency of scores at and below that point. And if you've got a class interval, if you've got a continuous variable, it's the frequency of scores below the upper true limit of the class interval you're interested in. And it is, we do it with cumulative f of x, is how we write it. Let's get to that here. First off, I want to point out what I was just saying, that we put the highest x at the top and count down. We had an instance of 0, but if the lowest instance we had was 2, you could have either started at 2, or because 0 is impossible, you could still start at 0. But cumulative is now looking from the bottom, it's going to count the number of scores that are at or below that point. So at 0 here, we've got 1 score. That's our frequency. So the number of scores at and below a score of 0 is 1, because there's just that 1 0. How about at 1? Well, at 1, there was 0 to add, so we still have the amount of scores at and below that point of 1, because there's that 1 0. There's no 1s and there's that 1 0. But let's look at 2 now. Well, 2, we had 3 to add, because there was 3 instances of 2. So we add that 3 to the 1, and we get 4. There are 4 scores at and below 2. There are 3 at 2, 0 at 1, and 1 at 0. So there are 4 total scores at or below an x of 2. Next, there are 4 scores at 3. So if we add that to the 4, we get 8. So there's 8 scores at 3 or less. The next, we can add 6 to that. We get 14. Add 8 for the 5, you get 22, all the way up. When you add 7, you get 29. You add 4, you get 33. 3, you get 36. 2, you get 38. And then finally 2, you get 40. One thing I want to point out here, though, is there's 40 scores at and below 10. Your number at the top here should be the exact same thing as your number at the bottom here, because they're the same thing. Your total number of scores is 40. Well, the number of scores at and below the highest point in your distribution, which is 10, is going to be 40. All scores are at and below 10. Hope that makes sense. If it doesn't make sense, talk to me in the review session. Next is relative frequency. Relative frequency is now going to be a proportion. It's also a probability, but we're going to look at it as a proportion for now. It's a proportion. We are going to convert our absolute frequency, our f of x, to a relative frequency. We convert it by taking our frequency and dividing it by n, which is the total number of scores. So if you recall from our example, n equals 20, or 40, sorry, n equals 40. So taking any absolute frequency, taking a specific frequency, and dividing by 40, you'll get the relative frequency. And we write it like this. Relative f of x, let's look at that. I'll actually be able to explain it better in the graph. So what we have here is our relative frequency column. So what you want to do is you want to take your frequency column and divide that by 40. So if we divide each of these by 40, again, 40 is our n equals 40, and relative frequency equals our f of x divided by n. This column right here is our f of x. We're just dividing each of these by n. And that gets us our relative f of x. So 2 divided by 40 is 0.05. Here, 2 divided by 40 is also 0.05. Let's go down to the bottom, or let's go to the middle. Here, 8 divided by 40, that's an easy one, that's 0.20. 0 divided by 40 is 0. 1 divided by 40 here is 0.025. So that's, you get the relative frequency by just dividing the f of x by n. Well, if we started with frequency, and then we did cumulative frequency, now we did relative frequency, can you guess what's next? If you guess cumulative relative frequency, you are correct. And this is going to just be the relative frequency of scores at or below that point, written as cumulative relative frequency f of x. Which gets us to this, cumulative relative f of x. There are two ways to get this. You can either take and add up the relative frequencies at and below that point. So, like for instance here, 0.025, well, it's just that. Why do we get 0.025 here? Well, we added 0 to it. Why did we get 0.1 here? Because we added 0.075. All the way up, if you add, let's say this 0.95 here, you add 0.05 to it, you get 1. That's one way to do it. Another way to do it, another way to get your cumulative relative frequency, is to divide your cumulative frequency, cumulative f of x, by n. If you don't want to do all that adding, you can just divide the cumulative frequency by n. You notice 40 divided by 40 here is 1. So cumulative relative f of x equals cumulative f of x divided by n. And another quirk you'll get here, in the relative frequency column, you notice at the bottom, if you add them all up, you get 1.000. You may get a number that is slightly different than this due to rounding errors. It doesn't matter what number you get. If you get 0.99, 0.98, 1.01, 1.02, something like that, doesn't matter what you get, still put 1.00 here because it totals 1.00 if you correct for rounding errors. But what you've got down here equals what's at the top here. And if you take your cumulative frequency and divide by n at the top, you're always going to get 1.00 here. If for some reason you get something slightly different because you added them going up like this, like I was saying, then if you get something slightly different there than 1.00, just that's rounding errors. Let's say like you get 1.02, 1.03, something like that. Just correct it to 1.00. I'm not going to mark you wrong for having it like that, but you should have it as 1.00 there and 1.00 on the bottom. You see there's two more columns to go. Let's look at those now. Next one is percent. Percent is very easy to do. Take your relative frequency and multiply by 100. So percent equals relative f of x times 100. And we just denote it by the percent symbol. So we've got the percent here, and again, percent equals relative f of x times 100. So take this relative f of x column here, multiply it by 100. Take me just a minute. Multiply each of those by 100, and you get what's in this percent column. So 0.05 times 100 is 5%. 0.1 here times 100 is 10%. Down here, 1 times 100 is 100%. That's what you should get at the bottom is 100%. Again, rounding errors might make you slightly off on this. You should still round it to 100%. Let's look at another one here. This 0.2 here times 100 is 20%. This 0.175 times 100 is 17.5%. Pretty easy there. And then can you guess what is coming up next? If we did the frequency, we did the cumulative frequency, we did the relative frequency, then we did the cumulative relative frequency, we did the percent. Now what do you guess is next? If you guessed cumulative percent, you were correct. So cumulative percent is just going to be the percentage of scores at or below that point. This is a good thing to know how to do, at least know how to understand what is going on, because when we start doing z-scores later, one of the things we will do is look at cumulative percents for z-scores. And essentially it's the percentage of all scores at or below that point. And you just add up the ones at and below that point, and you get cumulative percent. So if we look at this down here, 2.5%, that's because that's what's at and below that point. We're still at 2.5% because we added 0 to it. You could do all of these up to get all the way up to the 100% at the top, which again equals this 100% at the bottom. You can also get the cumulative percent by multiplying the cumulative relative frequency by 100. So there's two different ways to get that. So pretty easy to get there. You get to the cumulative percent by either multiplying the cumulative relative frequency by 100 or just adding up all of the percentages at and below that point. So if we looked at, let's just say this 55% here, well, it's going to be 20% here, plus 15%, plus 10%, plus 7.5, plus 0, plus 2.5. You add all those up and you get this 55%. Hopefully that's clear on how to do a full frequency distribution. This right here that you see is the full frequency distribution. All of our columns and rows are taken care of. If I were to give you just this row right here, you should be able to figure out everything else in this chart. Because again, just to get cumulative frequency, it's everything at and below that point. Relative is the frequency divided by n. Cumulative relative frequency is the relative frequency at and below that point. Percent is the relative frequency times 100. Cumulative percent is the cumulative relative frequency times 100. So if you were just given this right here, you can figure out all of the rest on your own. And you should be able to. If I gave you bits and pieces of this, you should actually be able to fill it in. So be sure to be able to do that on the homework, because on the exam, you're going to have to do that. One exception, and I wouldn't even call it an exception. I would call it something you do slightly different when you're doing a frequency distribution, is when you have too spread out of scores. If your scores are so spread out that your frequency distribution is going to be pages long. In the previous example, we had X scores between 0 and 10. But what if we had X scores between 0 and 100 or 0 and 1,000? You don't want to have 100 rows or 1,000 rows. So instead what we do is we do a grouped frequency distribution. We group together some of the X scores. We group them into equal groups, but we group together some of the X scores. So to make the data more understandable and more interpretable, we create a grouped frequency distribution by grouping the scores into mutually exclusive categories. I've used that word a few times now and I've defined it every time, but remember, this is going to be a good thing to know going forward on at least one of the exams, maybe not this first one, maybe the second one. I'm going to expect you to know the term mutually exclusive. Mutually exclusive means it can only be part of one category. So we're going to create a group frequency distribution where scores can only be in one category. They can't be in more than one category. And we're going to have classes, and a class is going to be a grouping. A class is defined as a mutually exclusive category that represents elements or data points that share a common characteristic. Basic for grouping observations that are similar to one another. I already defined mutually exclusive. It can only be in one category. We're basically going to do these. The common characteristic is going to be they're close together in number. So we're going to group them by numbers that are close together. So let's say we were looking at exam scores, we might group them together like 91 through 100, 81 through 90, 71 through 80, that type of thing. So we are grouping them in a way where the numbers are together that are close together are together in a group. How do we construct a group frequency distribution? Well, first off, how you construct it is up to you as a researcher. As the statistician, is up to you how you want to exactly group it. But there are some general guidelines or rules. First, find the range of scores from highest to lowest. So take the highest score in the distribution. Let's say we had a group of numbers and the lowest score is 48. We're talking about exam scores here, and the highest score was 99. You're going to take and do the highest minus the lowest plus 1. So in this case, we get 51 plus 1, so highest minus the lowest plus 1 is 52. So we've got the range. 52 is our range. The next thing we're going to do is take the range and divide by the number of class intervals we wish to use. So if we wanted to use, and again, this is up to you to decide the number of class intervals you want to use. On the homework or the exam, I'm going to tell you specifically how wide apart to make these class intervals, how many numbers to make each class interval. But if you were constructing it on your own, what you do next is take the number of intervals you wish to use to determine the size of them. So take our range, let's say we wanted 10 intervals. So we take the range and divide by 10, and what we end up with there, we wanted 10 intervals, so we get a number of right around 5. We get 5.2 to be exact, but let's say, so we've got that. Then we're gonna round it up, and now we're going to use a range of 6. Actually, let's just go down to 5. Again, this is what I mean by you can have these basic small differences. It's up to you as the researcher what you want to do. Let's say I want each interval to be 5 wide now that I've gotten more specific. And you can kind of see what happens here. List the limits of each class interval starting with the lowest score at the bottom. The lowest limit should be divisible by the size of the interval. I said I wanted the size of the interval here to be 5. Well, if it's not divisible by 5, then select the next lowest score that is. So the example here I have, but let's look at our example up here first. We had 48. We want the next lowest score that's divisible by 5. So we would actually start with 45 as our lowest number for class intervals. And we're going to end up doing essentially 45, because it's going to be 5 wide. We're going to do there 45 through 49 as our first class interval, which includes our lowest score. Let's say your lowest score was 43 though. It's not divisible by 5. So then if we were doing a intervals of 5 like this, we would then round down to 40, and we need to have 5 numbers in our lower limit. So what you do is you add your class interval number, the amount, the size of your class interval, you add that minus 1. Why do you add it minus 1? Because you've already got the lower number. Essentially, we've got 40, 41, 42, 43, and in this case 44 because we added 4 to it. So you've got 1, 2, 3, 4, 5 numbers in your class interval. The next limit is going to then start at the next lowest number, which is 45, and in actuality it would go up because remember you put higher numbers at the top, 45, 46, 47, 48, and 49. So here you would have 40 through 44. The next one would be 45 through 49, going up from there. All the way up as far as you're going. Let's say you were going all the way to 100, you'd keep going up all the way up to 100. And in this case, your last class interval, if you were going all the way to 100, your last class interval would not be 95 to 99 and then one that's just 100. You'd do your last one as 95 to 100, and that's where you can kind of break your rules where each class interval is the same size. If you've got a continuous variable, you do have to add your true limits on to it. So let's say we weren't just looking at these as whole numbers. Let's say you could have a possible fraction of a point on your score for this exam. Then the true limits would come into play. So in actuality, what you've got for this bottom one is 39.5 because we did plus and minus half of our value, 39.5 through 44.5. And then going all the way up from there because you're adding you added your true limits if you did it. On the homework, you do have to do one of those, or at least be able to understand what the true limits are around, like the highest and lowest score in a distribution, that type of thing. Then you would, just like a normal distribution, you'd tally the raw scores appropriate for each interval in the frequency column, but now it's the raw scores. Your frequency is the frequency that fit within each of these. So this is your x. The f of x is going to be the frequency in each of these intervals. So here it would be the frequency. Let me just erase this because that's just relating to the true limits. This here would be the frequency between 40 and 44. So let's say there were 3 scores there, you'd put a 3 there. It depends on how many are actually in the distribution. And then finally, you add up the tallies for the interval. Be sure that matches the number of data points you have. So add up your total of f of x of your frequencies just to make sure you've gotten your n and you've met all of the different scores. Let's look at an example. Those 41 exam scores that we talked about earlier in an example earlier when we did the stem and leaf plot. You get this group frequency distribution here. Just going back to it, the lowest score on that was a 38. The highest score was a 99. So the researcher doing this was interested in basically breaking them down into groups so that each one was 10. You'll notice that this last one is 11. That's just the way it works sometimes. Again, as I said, that's just sometimes the top one is going to get another score added to it just to make it even out. So you wouldn't have another category that's just 100. But here we've got 30 through 39, there was 1 instance. 40 through 49, there was 1. 50 through 59, there was 1. 60 through 69, there was 4. 70 through 79, there was 11. 80 through 89, there was 11. And then 90 through 100, there's 12. Then, of course, you do the cumulative, which is everything at and below that point. At 3 here, let's look at 50 to 59, there's 3. That's because there's 1, plus 1, plus 1. Everything at and below that point. And then you can just do the relative f of x, which again is f of x divided by n. So this one is 12 divided by 41, because we had an f of x there of 12 and n of 41. Your cumulative relative f of x is going to be everything at and below that point. You see here that if you just do rounding, you get 0.998. As I said, you should always write 1 there, just like you should write 1 down here. Just like when you do your percent, you should write 100%. The reason we get slightly different scores is just due to rounding. This next one is an important slide. This is a very important slide because it is looking at what is going on. So why do we convert these absolute frequencies to these proportions or relative frequencies or percentages? Why do we convert an absolute frequency to a relative frequency? Or why do we convert these absolute frequencies to a percent? And this is something you should think about for a minute. I'll let you think about it for just a second, and then I'll discuss it. You could even pause the video here and think about it for a minute and try and come up with an answer of why we convert frequencies to proportions and percentages. Okay, let's discuss it. We convert frequencies to relative frequencies or percentages because it allows us to compare two or more groups when the size of the groups is different. Let's say you have two different groups that are taking an exam. And in group 1, n equals 100. Group 2, n equals 1000. And they're taking a quiz, a 0 to 10 quiz. And you're trying to find the number of people that scored a 10. So when you look at, so in the first group, you had, let's say, 10 people that got a score of 10. Let's use a different number than 10. Let's say you've got 8 people that scored a score of 10. So the f of x for 10, the frequency of a score of 10, is equal to 8. Over here, the frequency of a score of 10, let's say, is 60. Which group did better? Which group had more 10s as a proportion of the whole? Well, when you look at just absolute frequencies, when you look here, we've got an 8 and a 60. Well, this group must have done better because they had more. They had 60 10s. This group only had 8 10s. But when you convert it to a proportion, when you convert it to a percent, you can see here that in this case, 8% got a 10, whereas down here only 6% got a 10. So in relative terms, this group, group 1, did better than group 2. So when you've got different size groups, converting these absolute frequencies to proportions or percentages, to relative frequencies or percentages, allows us to make a comparison. If you don't do that, you can't make a comparison. And later we'll talk about z-scores and how z-scores are essentially a way of making this type of frequency distribution where we make it relative. It's turning everything relative. It's what's referred to as standardizing. You're standardizing the scores by turning them into proportions or percentages, and that standardization allows you to make comparisons between two or more groups. So just in review, we looked at distributions of data and explained why we use descriptive statistics. We looked at data presentations and demonstrated proficiency with data presentations used. We also discriminated between bar graphs and histograms. And finally, we looked at frequency distributions and we constructed a frequency distribution. And hopefully each and every one of you can meet each of these 4 learning objectives now. Thanks. Come on back.